This morning, as I was getting a cup of coffee, there was a guy standing next to me that saw the name tag, and he says, "You coming to the summit?" I said, "Yes, I am." And he says, "What do you do?" I said, "I'm an industrial archaeologist." And he said, "Great. What is that?" Industrial archaeologists study industrial heritage, the physical remains of industry-related artifacts, sites, processes, and systems within their cultural and historical contexts. The case study for today's presentation illustrates this by example. Built in 1902, the Champion No. 4 is the earliest example of ore lifting and processing technology remaining from Michigan's copper mining era. This structure is a mechanism built specifically to raise skips of copper ore from thousands of feet underground, unload that ore into bins, distribute the ore to crushers powered by steam engine, and then transfer the resulting mineral to rail cars for shipment to a stamp mill located on Lake Superior at Freda, 14 miles distant. From 1902 to 1967, the No. 4 contributed to a local economy, providing a workplace for husbands and fathers of families living in Painesdale, Michigan. The International Committee for the Conservation of Industrial Heritage, TICI, is the world organization representing industrial heritage and is special advisor to ICOMOS on industrial heritage. In the charter presented to ICOMOS for ratification, TICI describes industrial heritage as the remains of an industrial culture which are the historical, technological, social, architectural, or of scientific value. By its mere existence, industrial heritage reminds us of previous ways of living or being in the world and elicits memories, discussion, and debate. This morning we're going to compare two results of missions conducted at two industrial sites that formed the basis of this presentation. To navigate the process, the project will be divided into three phases: results and then conclusions. Phase one was an experimental phase where observations were made at a rescue-type mission at the Cliff Mine Stamp Mill House and Washroom Archaeological Site, where wooden remains were very well preserved from being buried under stamp sand since we're not exactly sure, probably 1870. In phase two, the development, observations from the Cliff Mine were considered in conjunction with the needs of the Champion mine site to design a hybrid approach to data collection which would also support future technologies for heritage interpretation. In this phase, the typical laser scanning mission was taken apart to understand how the equipment and software worked, what it can do, what it can't do, and apply that knowledge to the needs of heritage. Then in phase three, 3D documentation, the challenge was to reassemble the components into an approach by which the capabilities of 3D digital documentation for preservation can be adapted to complement the interests of cultural heritage management by scanning from the archaeology. The results of the two missions will be compared and conclusions will be made. As we proceed, the technology term refers to the professional firms and other interests which may include private investors, foundations, and governmental institutions. Heritage includes the professions who represent the mission to encourage the study, interpretation, and preservation of historically significant industrial sites, structures, artifacts, and technologies. The design represents the rules and controls technology and heritage professionals will follow when conducting the 3D documentation mission. In the summer of 2011, an excavation was proceeding at the Cliff Mine site near Eagle Harbor, Michigan. The site presented a Cornish-influenced stamp mill that utilized non-industrial milling and ore washing technologies. The architecture presented evidence of extensive modification to the mineral washing process, showing newer technologies were integrated within existing constraints. The grooves eroded in the wood, maybe you can see them in the center of this slide, provide evidence the industrial archaeologist can use to determine and interpret how slope and speed of water relates to the amount of copper being produced by this process. The field school research team included students interested in the NEAT factor of a Lidar survey, and discussion of the complex architecture led to the desire to perform a Lidar mission. The hope was to create a virtual model to study the interrelated parts of the ore washing technology and provide a quick test of future collaborative opportunities between IAs and surveying student teams. The archaeologists agreed and arranged for Clearwater Surveying to conduct a survey pro bono. The team was led by a Michigan Tech graduate experienced with the operation of the Regal LMS Z420i long-range 3D terrestrial laser scanner. The 420 is a battery-powered long-range time-of-flight scanner tethered to a laptop running dedicated software. It has a Nikon D300 camera collecting RGB data to color the point cloud. It soon became apparent scanner placement would be compromised due to its mechanical design. The 2-meter minimum distance to work required for the scanner to be positioned away from the edge of the excavation. Compounding the problem, limited vertical angle of tilt restricted the scanner's ability to collect data in regions obstructed by architecture and depth of the excavation. On the second setup, the laptop power was exhausted, requiring the crew to remove the battery from their pickup, rig jumper cables with alligator clips, and then complete the remaining 4 scans. When the data was presented to the team leader, not only was he unsure of what to do with it, he didn't have software that could open the files. Observations from the Cliff Mine mission demonstrate a lack of communication and understanding about the scope of the project. While some good data was collected, it was not delivered in a usable format. Mechanical design of the scanner limited access to the archaeology, power problems caused unexpected downtime, and data was not delivered in a form the team leader could use. In fairness to Clearwater Surveying, they volunteered their time, the Regal was the only scanner available, and the project was outside their area of training and expertise. This said, a considerable amount of good data was collected, and the process provided an alternative method of documentation when time and complexity was a concern. The experience raises an important question for the archaeologist considering Lidar for documentation. If heritage and technology have difficulty communicating at this level, is other significant industrial and material culture being lost or failing to be documented? Considering the increased attention Lidar is getting in the marketplace, it can be argued that within the industry, there's a tendency for the technology to drive its use, or in this case, drive the bus. An internet search returns demos and videos taking viewer on tours around and through point clouds and 3D models. Typically, these firms are not connected to the mission statements or public interpretation concerns of heritage professionals. They may also lack awareness of how their data collection methods could impact new applications and distribution technologies being developed for the heritage sector. Complicating this are the instances where the technology is oversold and fails to deliver the expected wow factor. Heritage managers, on the other hand, may be unfamiliar with Lidar language, yet have a need to communicate the value and significance of their sites within the natural cultural setting and social context. This situation leads us to phase 2, development. In contrast to the Cliff Mine project, the terrestrial Lidar mission at the Champion No. 4 was designed to collect interior and exterior 3-dimensional data, which will be archived for documentation and preservation efforts, archaeological study of machinery, processes, artifacts, and other material culture for future production of media products used in heritage interpretation. I put this picture in here to give you an idea of the complexity present in the building. The Champion Mine site is owned by Painesdale Mine and Shaft Incorporated. There is no public access or interpretation. However, PM&S arranges chaperoned access to the ground floor upon request. The structure prevents significant integrity as evidenced by endless belts still connecting line shafts to the crushers, and hand tools hang where the workmen left them when the shaft house hoisted its last skip of rock on September 11, 1967. Manual controls are evident throughout the structure, suggesting the mining company made few improvements to modernize the facility throughout its period of operation. Now in phase 2 of the restoration project, a local engineering firm has been retained to complete a partial shaft house settlement study. And while the focus of this study is on soil erosion at the top of the shaft cap, a man skip is left in position from 1967, causing concern for the roof and supporting structure. PM&S is also accepting bids to measure and restore windows. This is complicated, of course, by the heights and the the poor quality of the floors in the building. Initial discussion with PM&S confirmed that while the organization lacked exposure to virtual or augmented realities, they considered digital presentation and marketing channels, including social media, necessary to their survival. PM&S also realizes funds are limited as current restoration and conservation efforts are consuming all monies received from membership donations and sales of cookbooks featuring ethnic recipes and collections of oral histories. The primary goal of this project was to assist PM&S by guiding a Lidar survey to collect data which may be used for preservation and be formatted into digital products to educate the public and enhance the enjoyment, respect, appreciation, and conservation of the Champion Mine site. A walkthrough and study of photographs reveals safety concerns, including missing steps and the rotting floors. There was no electrical service to the building, so visibility was poor, and adequate power for flashlights and equipment would be necessary. Exacerbating these concerns was the overriding requirement that the scanning would need to be completed in one day. The visual excavation identified types and location of machinery, material handling, production processes, and other material important for interpretation. To determine extra costs and consideration, an unscientific but workable plan was devised. The technician would approach the assignment as a surveyor, contracted to scan the building, and he was allowed to choose his preferred scanning locations. The industrial archaeologist then made suggestions after the data collector locations were chosen. Any variance was recorded as additional or modified scans. Phase 3 goes on to present an overview of the process. Bruce Bowditch of Leica Geosystems volunteered his time and equipment as he is interested in developing vertical markets for scanning equipment used in heritage. He's been with Leica for 7 years as plant sales executive representative scanning products for the eastern U.S., including Geosystems product sales and training. Before joining Leica, Bruce was manager of 3D laser scanning and pipeline services group at Holland Engineering, Inc. The industrial heritage interest will be represented by Painsdale Mine and Shaft, Inc. My position is that of an industrial archaeologist responsible for designing the Lidar mission and assisting PM&S with their restoration and preservation effort. The general concept is to determine preferred scanner locations and to capture archaeological data, such as the drop hammer and shiv and cable as seen in this part of the photo. We didn't understand how this worked until we actually looked at this piece. In this plot of the crusher floor, the dark circles indicate scanner placement to record the two 40-ton crushers and tools left against the wall. Another detail was revealed on the right side of the picture, the profile of ore remaining in the bin near an area where the wall to the ceiling wire. For the exterior, scanner positions were of course selected to capture the architecture and recesses and inside corners, such as seen in the center of this picture. Scanning was accomplished by a Leica HDS 7000. This ultra-high-speed phase-based laser scanner is capable of collecting more than 1 million points per second, but did not have the optional camera kit at that time, which applies the RGB values of the photo to the actual points. The lack of color capability wasn't an issue, as the interior would have required supplemental lighting, and this was not an option. Operating at eye level, it rotates 360 degrees horizontal. The vertical field of view is 320 degrees, collecting a dome of points overhead. This radial pattern has two important properties. First, the point cloud is most dense near the scanner, and second, lower resolution data is recommended at short distances. This knowledge can be used in a mission that specifies significant objects to be collected, such as this improvised rock-breaking hammer. These objects will receive an optimized scan based on best resolution and quality for the scan distance to target. In some instances, the level of detail is such that the scan can appear as a black and white historic photo, as seen here in the lower left. For media presentation, unified point clouds, processed in like a cyclone, can be exported to CloudWorks for animation within 3ds Max design. In the Max environment, point cloud models can also exist and interact with other computer-generated imagery, such as vegetation and historic landscapes. Throughout the day, a tally was kept of additional and modified scanning positions. The results were compared to provide a comparison of the two scanning placement theories. At the bottom, you'll notice that Bruce added scans. It was difficult to keep our interests separated, but after adding positions and working out the cooperative procedure, the mission moved more quickly. At one point, we were on the mezzanine, and we both noticed the ore car tipping feature on the skip road at the same time. The Cliff Mine stamp mill was an open-air excavation where the 3 crew members logged 6 scans in 6 hours and 20 minutes. In contrast, the 2-man team, plagued by missing steps, rotting floors, multiple levels, and ladders with loose rungs, collected 50 interior scans in 7 hours, plus 6 exterior scans in under 2 hours the night before. In this case, the additional time spent to acquire data for heritage added approximately 1 hour to the interior scanning day. Taking a look at what PM&S received at the end of the mission, they received a complete data set of exterior and interior framing that can be referenced and incorporated with existing hand and total station measurements. They have an inventory of windows and sizes to obtain bids on window replacement costs, an inventory of rotting or missing floorboards and steps. Scanning for heritage complemented the structural survey by collecting reflectivity of subtle rust patterns of internal and external sheeting. Note that this was achieved without any supplemental lighting. PM&S will have a unified point cloud to be viewed in a point cloud viewer and file conversion for modeling in 3ds Max design. Use will also extend to provide cutaways of the shaft house to use for structural analysis. As you can see in this image, the beams above in this area where the mancar is hanging are deflecting. PM&S will also receive data in a form to be used for marketing and products for heritage interpretation. I brought along an example of what can be done with this. So this is not a part of the discussion, but if you'd like to know more about it, this is a 3D print model of one of these historic mine shaft houses. Before concluding this presentation, I'd like to acknowledge Painesdale Mine and Shaft, Inc. for allowing us to use the building for the study, and thank Bruce Bowditch and Leica Geosystems for the time and commitment that was applied to this effort. This snapshot of the Amique No. 2 shaft house meeting its demise is the laser scan of 1966. Without physical reminders of previous ways of living and being in the world, the ability to read the past is impoverished. While industrial structures present significant challenges for documentation and preservation, they offer significant opportunities for the industrial archaeologist to recognize the working class life and acknowledgments that something important went on in there. Heritage managers and digital documentarians have the opportunity to see the same subject and cooperate to document it digitally in 3D. John Cage, a pioneer of the non-standard use of musical instruments, wrote, "I can't understand why people are frightened of new ideas. I'm frightened of the old ones." Thank you.